Hi, everybody. This is your first mini lecture of the semester. Over the course of the next few mini lectures, we're going to be talking about oscillations and waves. This is important because we're going to start talking about light. And in some ways, we can think about light as a wave. And this also is a good way to start because it ties in with waves that we talked about at the end of last semester a little bit, how we thought a little bit about simple harmonic motion in lab, and we also talked about sound, and sound is a wave too. So here, real quick, is a fun little animation that I like to show, which illustrates waves in a different way than we might think about them. This is waves and oscillations as we can think about them in astronomy. Here we have two black holes that are colliding. And when these black holes collide, they send out a ripple on the fabric of space-time, a literal wave on the fabric of space-time. That's what we're seeing right here. And that wave has peaks, it has troughs, it has a speed, it has a frequency, it has a wavelength. And we can think about everything that we can talk about with waves, we can talk about with what we call these gravitational waves, where these massive black holes collide and literally they send out ripples on the fabric of space-time, oscillations. We're not going to focus on this here, but if you were in my astronomy class, you would learn a little bit more about these gravitational waves. Waves are important. One of the key points here is that waves transport information. Waves carry information. So this information moves outward and away from the source, and this wave, this information, makes a wave shape or an oscillatory pattern. And so we're going to think about this wave shape and oscillatory patterns over the course of the next few mini lectures. Now, all waves transport energy or information with them as they travel. So at the end of last semester, we talked about sound. Sound is transverse waves, where you have a compression of the air or the material through which that wave is moving, and you have an expansion or rarefaction of that material through which the wave is moving. So it's like if you take a slinky and you move the slinky in and out, you see those waves traveling across from left to right. But when we think about what we call longitudinal waves, which are like waves on a string, or waves that you can set up, like for instance, in the slinky, whenever you oscillate it up and down, like we did in lab last semester, that's a longitudinal wave. That's how light waves behave. There are many examples of waves in physics. We have oscillations when we're thinking about simple harmonic motion, okay? And that's just a description of the position of an object in time. But we also have physical mechanical waves. Those are water waves, sound waves, seismic waves, like when you think about an earthquake, waves on a string. Then we also have electromagnetic waves. When you hear the word electromagnetic wave, we're talking about light. Light is part of what we call the electromagnetic spectrum. Light is all parts of the electromagnetic spectrum. There's just a little tiny window of that electromagnetic spectrum that we can see with our eyes, and we call that visible wavelengths of light. So here I'm looking at some of our PHET simulations, which we're going to be playing with more in lab during our first lab rotation segment for your at-home lab. But let's look at some of these waves just to remind you about waves. So this is going to be like a wave on water, a ripple, a wave across water. So here I've started the wave pattern by dropping this little droplet of water into a pool of water. And here we have the wave propagating outward from the source, okay? And so what I can do is I can show the graph here. This shows, well, here in this graph, we're looking at the water level and how the water level oscillates as that wave is moving outward and away from the source. So this graph here is mapping the height of essentially the trough and peaks of that wave ripple as it's moving across the surface of the water. As you can see that it looks kind of like a sine or cosine pattern, a sinusoidal pattern. Now let's look at sound. And we talked about sound last semester. So in order to create sound, you have this speaker membrane that oscillates back and forth, that sends out compressions and rarefactions in the air to create the wave. And then let's look at light. So here I'm turning on my laser. If we think about light as a wave, that wave leaves from the laser. These bright green rings, you can think about that as being a peak of the oscillating wave pattern. And these dark points are the troughs of that wave pattern. And so you can really see this wave pattern here. And the thing that we map out, the amplitude of this wave, is the electromagnetic field, or usually we map the electric field, and the magnetic field oscillates perpendicular to that. So here we're seeing the oscillation of the electric field as that wave propagates outward. And that is exactly what we're mapping when we think about light as a wave. We've seen that these wave patterns are oscillatory. An oscillation is just a repetitive motion around some equilibrium position. In all those graphs, we had some place where we said, this is equal to 0. The amplitude, which we're going to be seeing written as capital A, or sometimes your book will use capital X, is the maximum displacement from equilibrium for that amplitude. And then the period that we call capital T is the time for one cycle or one complete repetition of this oscillation. And the frequency of this wave is 1 over the period. It's the inverse of the period. So you can think about the frequency as being the number of cycles per second, the number of these full periods per second that pass any given point. So the frequency of our wave is given in units of hertz, which are also units of the inverse second, 1 over second. And we can think about that because if frequency is a unit of 1 over time, okay, that has to be 1 over a second. And we give that a special name of hertz. It's spelled H-E-R-T-Z, or abbreviated as capital H-Z. Okay, and so for an oscillation, the time to complete one full cycle is the period of that oscillation. So here we're looking at a graph of, this is a cosine wave, okay? And we've got the amplitude or the position on the vertical axis, the horizontal axis is in time. So the period for this wave is the time it takes to complete one full repetition of this wave. And so we can look here and see just how far do we have to go in time before the shape of that wave repeats itself. That's the period. Here's an example of an oscillatory pattern in your heart, in heartbeats. On the vertical axis, we have the voltage across your chest when you're measuring your heartbeat, because the heart operates with electricity as well, really. It's just like a part of a circuit. So if you measure the voltage, the electric voltage across your chest for your heart, you can learn about how your heart beats, and you can measure those beats. So if you measure the voltage across the chest as a function of time, we see successive beats here. These successive beats of the heart signal produce the same period T in their oscillation. We see these nice peaks here. So if you've ever had an electrocardiogram, you would see a graph kind of like this. I've had many in my lifetime, and then they will tell the doctor about what's going on with your heartbeat and see if there's any irregularities. So the graph of an oscillatory motion has this form of a cosine function or a sine function. I know it says cosine only on the slide, but it can take on a sine or cosine shape depending on the problem that we're working with. A graph or a function that has the form of a sine or cosine is what we call sinusoidal. So these waves are all sinusoidal oscillations. Simple harmonic motion, sinusoidal oscillation. And so here we're showing simple harmonic motion by, let's say you have a bowl, okay, a bowl, and then you put a marble on one side of that bowl and you let it go. And then that marble on its own is going to oscillate back and forth, back and forth, back and forth along the inside of that bowl, okay? So it's displacement away from equilibriums, equilibrium's the place where that marble naturally wants to be. And so its displacement away from equilibrium is what we map on the vertical axis, okay? And on the horizontal axis is time. So to start with, our marble is at the top of the bowl. It has maximum amplitude. It's going to swing down, and when it passes through the equilibrium position, it passes through 0 here. And then it swings up to the other side of the bowl. We're going to call that here a negative amplitude. Well, it's on the opposite side of the equilibrium position from where it started. And then it's going to swing back through the bottom of the bowl equilibrium and come back up again. And if there's no friction, that marble will keep on going forever and ever and ever. So here's another example of simple harmonic motion. 2 examples. We've got a thing on a spring and a thing on a string, which you guys both played with last semester in lab. Okay, so let's say we have a mass and we've attached it to a spring horizontally. That spring is attached to the wall. Okay, so so if you just let the object go and don't touch it, right, it's just gonna wanna sit in its equilibrium position, happily not oscillating, okay? And so that position is 0. We're gonna mark it as 0 here, but you have to pull it away, that mass on the spring, away from equilibrium in order to let it go, to let it start oscillating, okay? So we're gonna pull that mass to its maximum amplitude and let it go. So here it has its maximum amplitude, and then we know that springs have a restoring force. So that spring is going to want to pull that object back through equilibrium. So then our mass is going to go back through equilibrium, and that maps out here on the shape of this curve as this kind of cosine pattern. We're swinging back through equilibrium, and then the mass reaches the other side, the amplitude, maximum amplitude on the other side of equilibrium. That would be our negative maximum amplitude. And then it's gonna wanna come back through equilibrium again. And so then we get this nice sinusoidal pattern. And you can also do the same thing with the pendulum. You pull back the pendulum away from its equilibrium position and let it go, and it's gonna oscillate back and forth. All of those oscillations can be represented by a cosine function or a sine function, okay, depending on what you want to do. Usually we start simple harmonic motion with the cosine function, because cosine starts with at t is equal to 0, you have maximum amplitude. Sine starts with t is equal to 0, you have 0 amplitude. So it just depends on the type of problem that you're working on. So it's been a while since you all have thought about sine and cosine, probably at least to map them and visualize them graphically.
It's probably been a while since the last time you thought about what a sine or cosine function looks like or how to graph one. And so we're going to take a look at this sinusoidal function here, the one that looks like sine. And for us, remember that these functions are representative of the position of a wave or a particle or a mass around some equilibrium position. A is the amplitude of that oscillation, and we've got the sine or cosine, depending on our problem. And inside the sine or the cosine, we have this argument called, which is 2 pi times the time t over big T. Big T is the period of our oscillation. Okay, so we're going to graph out the sine function here at a couple of different times. We're going to look at it at time is equal to 1/4 the period t, time is equal to 1/2 the period t, 3/4 the period t, and the full period t. Okay, so how to evaluate this function? We'll start with time t equals 0. So x, which is our vertical axis here, equals, I'm just going to call our amplitude, just leave it as a, sine of 2 pi times the time we're evaluating our function at, which is 0, all over the period. And I'm just going to leave that as big T. Okay, so we've got sine, and inside the sine argument, we've got 2 pi times 0. So this is really just sine of 0. And sine of 0 is equal to 0. So we've got a times 0, and that's 0. So at time t is equal to 0, our position is at 0 on the axis. Okay, so then let's try t is equal to 1/4 of the period. X is equal to a sine 2 pi times, so the time that we're evaluating it at, little t, is 1/4 of the period, and then we have to divide that by the period t. Okay, so inside our sine argument, we see that the big T cancels on top and bottom. So then inside the argument, we're left with 2 pi times 1/4. Okay, 2 pi times 1/4, that's the same thing as 2 pi divided by 4. 2 pi over 4 reduces to pi over 2. So this is the sine of pi over 2. And the sine of pi over 2 is equal to 1. So at time that's equal to 1/4 of the period of oscillation, our position is going to be A, the maximum amplitude, times 1. So our position is going to be A, the maximum amplitude. So for a sine function, we achieve maximum amplitude of our wave or our oscillation at 1/4 of the period. Then I'll leave it as an exercise to the reader in order to determine what is the position of our oscillation at time t is equal to 1/2 the period, t is equal to 3/4 the period, or t is equal to the full period. You would do the exact same process that we just did here, swapping out the little t in this equation right here with either, again, 1/2 the period, 3/4 the period, or the full period. And if we do that, we find that at 1/2 the period, our position is going to be 0. At t is equal to 3/4 the period, our position is going to be equal to minus a. It's going to be the maximum amplitude, but in the negative x direction. And at t is equal to the full period, we get back to where we started again, and then we have that our position is equal to 0. So let's go over here and plug these in. We've already got our position in here for where we are when t is equal to 1/4 the period, and where t is equal to 0. When time is equal to 1/2 the period, we have x is equal to 0. We pass through the axis. At time t is equal to 3/4 the period, we're at negative a down here. And then at time t is equal to the period, we're back over here again, okay, along the x-axis. So if I connect the dots here, we get our sine function, okay? So the sine function takes on values of 0 at time is equal to 0, at half the period, and at the full period, okay, of oscillation. And it takes on values of maximum amplitude, or absolute value of that maximum amplitude at time t is equal to 1/4 the period and t is equal to 3/4 the period. If I asked you to perform this same exercise for the cosine function, you would find that the shape of that wave looks a little bit different because we start at a different position along the x-axis when t is equal to 0.
In simple harmonic motion, the position versus time graph for oscillatory motion, or the position function for oscillatory motion, generally, again, for simple harmonic motion, is a cosine function. We choose this because the mass has to first be displaced from equilibrium. So at t is equal to 0, we want to have our position to correspond to the maximum amplitude. And for a cosine function at t is equal to 0, you have your maximum amplitude. So here's our function for simple harmonic motion. Our position as a function of time is equal to the maximum amplitude times cosine of 2 pi times little t over big T. But we also learned that you can write, well, the frequency of the wave is equal to 1 over the period. So you could replace the 1 over t with the frequency. And so then you could also write the equation for a simple harmonic motion as a cosine of 2 pi times the frequency times time. So anything inside this parentheses, when you're typing these things into your calculator, you have to say cosine And then you multiply 2 times pi times f times t, and then you close the parentheses. So we say all of this stuff is inside the argument of the cosine. Now that we've gone through an example of evaluating a sine function, let's evaluate a cosine function for simple harmonic motion. We are going to evaluate the position function for an object in simple harmonic motion. So here we have an equation for the displacement of a mass on a spring from its equilibrium position. So the position as a function of time equals a cosine, and then inside the argument of the cosine, we've got 2 pi t over the period. So if the amplitude of our simple harmonic motion is 10 centimeters, and the period of the oscillation is 10 seconds, that's big T here, what you could do on your own is sketch the mass's displacement versus time graph using these following points in time. So for T is equal to any of these time in seconds, what is your position along the x-axis? And so you could make a graph where the vertical axis is position and the horizontal axis is time, and you could plot all of these points, okay? And you can do that to show to yourself, what does this cosine function look like? But what I'm going to ask you to talk about is at what times, which of these times listed right here, is the amplitude of our oscillation 0? And at which of these times listed here is the amplitude of our oscillation plus or minus 10 centimeters? Now, the last thing that we're going to talk about is the energy in simple harmonic motion. This combines a little bit of our discussion with conservation of energy last semester with waves and simple harmonic motion now. So if you remember, the potential energy for a mass on a spring, here it's represented as U, but usually I wrote it as capital PE sub S, spring potential energy. So the spring potential energy, the energy you can store up in a spring when you compress it or expand it, stretch it out, is 1/2 K, where K is the spring constant, times x squared, where this x is your displacement of the mass away from the equilibrium position of the spring. So from conservation of energy, we showed that the energy, the sum total of energy, the kinetic and the potential energies at any point in time have to equal each other. So our kinetic energy plus our spring potential energy has to equal the kinetic energy plus the spring potential energy at a later time. So the sum of all of those has to be a constant. So our spring potential energy is 1/2 kx squared. Our kinetic energy is 1/2 mv squared. M is the mass, v is the speed. Then let's look at the conservation of energy when we're thinking about simple harmonic motion on a spring. So here we have our mass on a spring, and we've stretched it out, and we're going to let it go. At this point, when we fully stretched it out, before we let the spring go, it only has spring potential energy, no kinetic energy. When we let it go, when that mass passes through its equilibrium position, it has its greatest kinetic energy. Why? Because when it passes through its equilibrium position, it's back to its original length that that spring started from. So its spring potential energy is 0. And then whenever that spring pushes over to its maximum amplitude on the other side, it stops for a second. It has no kinetic energy and has converted all that kinetic energy it had when it passed through equilibrium into spring potential energy again. Okay, so you have your greatest, and down here's the plot of the spring potential energy, which is the blue, and the kinetic energy, which is the green here, as our spring oscillates, okay? So you have maximum spring potential energy whenever the mass is at its greatest elongation on one side of the equilibrium position and its greatest elongation on the other side. And whenever it passes through equilibrium, all of that spring potential energy gets converted to kinetic energy right when it passes through equilibrium. So that means when our mass passes through equilibrium, its maximum speed occurs there because all of its spring potential energy has been converted to kinetic energy. If we want to think about how we could calculate what is that maximum speed when our mass passes through equilibrium, well, we said that maximum speed happens when all of that stored spring potential energy gets converted into kinetic energy. So you want to set your spring potential energy 1/2 kx squared equal to the kinetic energy 1/2 mv squared. So the 1/2s cancel on both sides. And so you could solve this equation right here for the maximum velocity, maximum speed that your mass will have when it passes through equilibrium. And this is going to be a workbook problem for you, is finding that maximum speed by using this relationship and solving for v.